Hello guys, so today we are going to start Leetcode questions of uh, 790, and this questions belongs to Domino and Tromino tiling. So let's understand the question first. Okay, so let me give a pen. It's fine, we'll take a later. Okay, so the question is saying that you have two types of tiles, a 2 cross n domino shape and a Tromino shape. Okay, so this is your domino shape and this is your Tromino shape. Okay, so you may rotate these shapes. Okay, these shapes can be rotated as per the question saying. Okay, so given an integer n, return the number of ways to tiles to return the number of ways to tile on 2 cross n board. Since the answer may be very large, return it modulo 10 to the power 9 plus 7. In tiling, every square must be covered by a tile. Two tiling are different if and only if there are four directionally adjacent cells on the board, such that exactly one of the tiling has both square occupied by tiles, you can say. Okay, so for every tiles two tilings are different. Okay, as you can see, two tilings are different. So if and only if there are four directionally, right, there are four directionally adjacent cells on the board, such that exactly one of the tiles has both squares occupied, like this side and this other side should be occupied. Okay, and similarly you can see that at least two sides are occupied. This side is occupied, this side is occupied. In all the places you can see both at least two sides are occupied. Okay, so both square occupied by tiles. Now if we pass one, means we have to return only one. Otherwise, if we have n equal to 3, means we are passing three tiles, then we have to return 5. How? So you can see that these tiles and these tiles, right? So in this tile, every square must be, it is saying every square must be covered by a tile, right? And two tiling are different if and only if there are four directionally adjacent cells, right, in the board. And as you can see, this board is tiles with this one, this is with this one, and similarly with this other one, right? Okay, so one of the tiling has both square occupied by tiles. So this square is occupied, this square is occupied. If you talk about white one, this is occupied, right? Means completely bind with at least two sides, you can say. And if we'll check this, so total combination is what? Total we are passing 3, right? 3 combination we are passing. So total is 5 different ways we can do that, like this and this. Okay, total, so we are passing actually 3. So initially you can see that we are passing 3, right? So 3 and in this 3, right? So it will be what? Our one combination. If we pass, like if we will rotate this, so this will this one. If we will rotate like this, then it will become like this, and so on. We can do that, or at least 2 we can do that, right? At least 2 combination we can do that. Okay, that's all. Okay, so we have to understand the objective, right? Give me pen. What is the objective of this program? So objective of this question is follow. We can say count how many ways to completely fill 2 cross n board, right? If there is a 2 cross n board, right? So how many ways this matrix can be filled, right? This matrix can be filled by using two shapes, right? Two shapes. How many ways? One, two dominoes, right? Two cross one is a dominoes, right? And L shape is what? L shape is domino, right? This is, you can see that this is 2 cross 1, right? This is 2 cross 1. Dominoes are 2 cross 1, but this one is L shape. This is L shape, correct? So now note, we have to also note that the rotation of these shapes are allowed, right? So if this is like this is a straightforward 2 cross n is like this one. So we can do like this, what? We can rotate like this, Gotcha? Got it? And otherwise, if this is like this, so we can rotate like this. So initially it is like this shape, right? We are doing like this, right? Now it has been rotated, right? Correct. So at first glance, one might consider testing every possible combination of domino and tromino and then count the one that has completely filled 2 cross n. Correct. So the 2 cross n board. So this can be achieved through backtracking, right? We can do using by backtracking. Let's see, backtracking. So you know that in the backtracking, where we fill the board from left to right, if there is a board, we can take 2 cross n, there is right. So if we'll talk about, so there is, if this is 2 cross n, right, like this, so what we can do that, so we will fill the board from left to right, from left to right. Okay, if this is left, right, and this is right. Okay, so we will fill the board from left to right, and at each step we try all the valid ways to place a domino or tromino. Once the board is full or no tile will fit in the remaining space, right? So what we can do, we will remove the last tiles placed, backtracking, okay, to return the previous board state. So try all the remaining tiles placement options as you can imagine, and construct every possible board. Would be a time consuming process, but you will understand. So for the most, we are not actually interested in finding every possible way to completely fill the board, but we are only interested in the number of ways the board can be completely filled. With this in mind, there should be more efficient way to solve the problem. It seems like we are stuck now. What else can we do to solve the problem? So whenever you are not sure how to approach a problem, it's good idea to draw out the first couple of scenario. Okay, so if we'll talk about the scenario, right, though first, if this is 0, right, at k it's 0, let's assume k is 0. So initial value is what? Initial value is nothing but this is not filled correctly. And if we'll talk about, there is one k is 1, means tiles is 1. So what will happen? There is one tiles at least we have, right? And if we will talk about, there is two tiles, right? If, let me clean as well, we'll talk about later. I think from here we can clean. Sorry. Yeah. So let's erase everything now. We're doing backtracking only, right? So what I was saying that previously, if we have k is 0, means we don't have anything here, right? But when we have k equal to 1, let's k tiles, number of tiles, so we have at least one tiles here, right? And when we talk about k equal to 2, the representation is either this one or this one, you can say. But if we have k equal to 2, means we can place tiles either horizontally, vertically, or horizontally, right? Correct. So or if we talk about, if number of tiles we have here 3, right? So what we'll have, either we will store like this, these 3 tiles, right? Or we can make a combination of 2 tiles here like this, and 2 is horizontally and 1 is vertically. Another we can take what? One horizontal, one vertical, and two horizontal. Sorry, like this. Okay. So this is also a combination, right? So three we have taken vertically, right? Another two is we have taken what? Another two we have taken as this one, right? And another three, in three we have taken this one, right? So this can be a any way, right? We can make this a very good approach, right? Or there is also another approach we can take, like this, right? We can make a combination like this, right? So if actually like this, right? We can say L shape, right? This is L shape. And another can be what? Like this. We have L shape, right? So we'll do like this. So total, if k equal to 3, so this is our combinations, right? These are the combinations. When k equal to 2, there is two combinations only, horizontally or vertically. When we have k equal to 1, there is only one combination. And when k is not, right, then there is no combinations, right? So take a closer look at the at these pictures, right, that I have drawn. So you have to notice that for a board with width k, this is width k, right? Some of the possible tilings can be directly be drawn from the two previous fully covered board, right? Or what I can tell you, give me 1 minute. Or yeah, done. So let me take the pen again. So either what we can do these things, right? Or if we will assume k equal to 3. Okay, so new tiling can be added, right? So new tiling can be added. How we can add? By one vertical. We can take one vertical domino, right? We can take one vertical domino to the k minus 1, right? How will take that? So if we have k equal to 2, right, means what? If we have k equal to 2, means we have one combination and another combination, right? This one. So both are horizontally. But when we are taking k equal to what? 3, means I am talking about we have 3, right? This is k equal to 3. Got it? Now because we have added one vertical domino to k minus 1, this was only 2, now we have added k equal to, now k equal to 3, means we have to add one vertical domino in this one, right? But when we are when we have k equal to what? 3 only, like this, k equal to 3 only, and we want to add a new tiling by adding two horizontal domino, right? Ever we have added only one vertical, but here we will add two domino tile to k minus 2. How we'll do that? So we know that k is what? K is 3, k equal to 1, sorry, k equal to 1, and we have like this, right? So when we are adding two horizontal domino, so it will look like what? We have one horizontal already, so we will add horizontal one like this, correct? So these are the possibilities that we are doing, right? However, the sum of the possible tilings cannot be derived from previous fully covered board, right? Directly, you can say. So instead they must be derived from a partial covered board with width of k minus 1, as we have seen here, right? Or what we can do, we can draw it. Wait 1 minute. Okay. Okay, very good. There is another option. Yeah. So what we can do, a fully covered board of k equal to 3 can be derived from a partially covered board of width k equal to 3. Sorry, I'm talking about if we have k equal to 3, right? What I'm talking about, if k is fully covered board, right? K equal to 3. This is the width of what? Board, and can be derived from a partially covered board of what? K equal to 2. We can derive from this to this, right? This board to this board, right? How we can do that? How we can do that? When we have k equal to 3, new tiling by adding one what? One L shape. We are taking one L shape Tromino, right? We are doing one Tromino to k minus 1, right? There is one L shape Tromino to k minus 1 we will add, and then we can make, right? So Tromino will look like what? Right? L shape, right? This is L shape. And we have k equal to 2. I'm talking about k minus 1, right? So if we are going to build k equal to 3, then if we'll do k minus 1 means what? This one. So this is L shape, right? So in the L shape, if we have the k minus 1 means this is the L shape we are talking about. We have k equal to like this one. From here to here, we will make like this, and another half L shape, right? We can add how? We can add like this, right? So this will be our k equal to 3. So we have to understand like how we can make the possibility as, right? So what we can say that some of the possibility tiling cannot be derived from the previous fully covered board directly, right? So instead they must be derived from the partial covered board with a width of k minus 1, right? So if we are going to make k equal to 3, so this is our k minus 1, right? So from k minus 1, if we will add something like L shape we are adding here, right? So what we are making? We are making this one, right? So we can say that a fully covered board of width k equal to 3 can be derived from a partially covered board of width k equal to 2, and that we can see here, right? So this provides us a basic idea of where the possible timings, basic possibility, right? And we can possible tilings we can understand, right? So the possible tilings come from a board with a width of k, right? So let's find out. Give me 1 minute. I'll clean this. Okay. Yeah. So what we can do? So let's find out how we can derive an algorithm from these patterns, right? So now let's define a fully covered board, right? A fully covered board, right? And all tiles on board are covered by either two things, domino or tromino. And tromino can be what? Partial covered you can say partial covered board, right? And same can be fully covered, or this can be fully covered, right? Fully covered board, right? Except leave the tiles in the upper right corner uncovered. So what we can do, a board with only the lower right corner, right? Upper right corner we are talking about like this, right? We have, right? So we are not covering this one, we are taking only this part, correct? So what we can do, the upper right corner or lower right corner uncovered is also covered. So this we can say partially covered, that we have seen the previous example, right? So however, we will discover soon, and we do not need to keep track of which corner is uncovered or not, right? So because we have symmetry, if we'll take symmetry f of k, correct, the number of ways to fully cover a board, this is the number of ways fully cover a board with width width k. What is the width? K. So this is nothing but f of k, right? Sorry, this is the symmetry, this is symmetry, but this will be our, if we'll take another pk, right? P of k we can take. So this is our symmetry we can take, and this is our fully covered board has been covered in number of ways, that is width k. So we can determine the number of ways to a fully or partially tiles of a width k by considering every possible ways to arrive at what, either f of k or p of k, correct? Either both of them, by placing either a domino or a tromino. So if we, sorry, let's find f of k together, right? So how we will find this f of k? And you can pause to the practice by finding, you can also find by p of k on your own, you can do that. So all of the ways to arrive at the fully tiles board of k, right, that we are talking about, fully tiles of width k, right? There is two possibility, right? If I write here, if I'm going to write here, right, what will happen? Either we will form f of k minus 1, correct? In this, what we will do, we can add one vertical domino for each tiling in a fully covered board with a width of k minus 1, right? And if we will talk about this form, we will from f of k minus 2. So in this we will add two horizontal domino. Here I was adding one vertical domino, right? Or here I was adding what? Two horizontal domino, right? So for each tiling in a fully covered board with k minus 2, we are adding what? Two horizontal, and for this one I am using one vertical. So what we have to note, that we don't need to add two vertical domino to f of k minus 2, since f of k minus 1 will cover that case, and it will cause duplicate, correct? Because we are already adding one domino. So when we are calculating for this one, we have to see that we have already added one domino, and this will be your duplicate count, right? So we have to count it again, right? So give me 1 minute. I will clean from here. Okay, I think I can clean this one also, right? So if we will talk about from p of k minus 1, right? So here we can add one else if. What? We can add one else if Tromino. From f of k minus 1 and f of k minus 2, I was adding one horizontal and two vertical domino, right? Where if we'll talk about k minus 2, so if we have already added k minus 1, where one domino is we have added, so we are adding duplicate domino, right? But from k minus 2, sorry, for k minus 1, we can add one else Tromino for each tiling in a partial covered board, correct? Where partial covered board, that we have already seen the example, right? From we are calculating k equal to 3, right? So we are doing k minus 1, we are adding one else if, and then we are doing, right? So from p of k minus 1, we will use one else if, right, Tromino. So what we will do, we can add one else if for all this partial cover, right? And the width is nothing but what? K minus 1. So what we can do, we will multiply p of k, this one, by 2, multiply by 2. The ever one, p of k minus 1, we can multiply by 2, because for any partial covered tiling there will be a horizontal symmetry, correct? Like if I write this is our L shape, right? So the horizontal symmetry is what we have, like this, sorry, like this only. Give me 1 minute. This is the issue with the writing pen. I'm sorry, right? So if this is like this, the horizontal symmetry is what? Like this. This is exactly equal, correct? So for example, if we take 2 p k minus 1, right? Both state that identical and reflect over the horizontal edge of the board, right? Like this, this will be reflect, right, over the horizontal edge of the board. Logically there must be an equal number of ways to fully tiles the board from this one, p of k minus 1 state. So rather than count the number of ways twice, we simply multiply the number of ways from p of k minus 1, and then we will multiply by these two, correct? So if we will do the summing, what will happen? This is the k value, and f of k minus 1 will do f of k minus 2, and plus we will do 2 into p of k minus 1. So I think this is our equation. To count, to get the number of ways to reach total width of k of the board, right? Okay. So give me 1 minute. So let me remove this one. So what I would, let me remove this one also. Right. So if I'm going to write k equal to 2, right, and this is horizontally symmetry. This is horizontally symmetry, right? This is horizontally symmetry arrangement of what? P of k. Okay. So if we are taking P of 2, means P of 2 we are doing, right? So this is your L shape. Look like this, right? This is your L shape, look like this, and we will make this symmetry arrangement like this. What? Either if we'll do symmetry, this will look like this. Then we can say that of this one we have the horizontal flip, right? Horizontal, you can say flip, right? This is our horizontal flip, like this, if we'll do that. Okay. So now we note that where tilings of f of k are coming from about p of k, right? So can we apply the same logic and find out? Absolutely yes. Then take a pen and start drawing scenario that contribute to p of k, and that is p of 4. So actually this is a good technique to add critical thinking during the interview. So start by drawing p of 4, and remember p of 4 is a board of width 4 with the first 3 column, right, and fully covered, and the last half covered. So now try removing domino or a tromino to find the scenario of this one. So if we talk about this, is already we have, this is our domino, but if we'll talk about tromino, right, we already have like this, right? So now try removing a domino tromino to find the scenario to contribute to p of 4, right? So notice this p of k can come from the what? Adding a tromino to a fully covered board of k minus 2, k minus 2 plus 1, this one, right? We can do. So adding a horizontal domino to a partial covered board of k minus 1, that is nothing but what? P of k minus 1, correct? So we can say that if we are going to calculate conclusion of P of k, right? So this is nothing but what? P of k is P of k minus 1 plus f of k minus 2. So this is our example. This is our two conclusion have for f of k and for p of k. So we'll see our dynamic programming here. I'm using dynamic programming approach to resolve this problem, right? So what we have intuition here, we will use two transition function, right, and a recurrence relation. We will use two transition function as the recurrence relation. Okay, so then we will create a recursive solution from f of n to bottom, right, to the bottom. So base case described in the algorithm section, since it's generally more intuitive to solve the dynamic programming in a top-down manner. Additionally, to avoid repeated calculations, we will memorize the result of each subproblem by storing the calculated result in two maps. So we'll take f of cache and p cache. So both cache will store the results of subproblem. So what we can do, we will start of f of n and then drive all the ways down to the base cases, f of 1, f of 2, f of and p of 2, you can say, and we will use the same definition f and p from the overview section, right? So we will use f of k and p of k. F of k we will use for the fully covered board, number of ways to fully covered board of width k, and p of k is the number of ways to the partially covered board of width k, right? And then we will see the recursive calls, and we will use the result of subproblems and the base case to help us to get the final result, right? So let's start from here. Okay, so we have to take a value mod and we'll take 2 cache memory that will store our subproblems. Then what we'll do, we will check in the cache. If that contains, then we will return from there. We do not need to recalculate. Or if n equal to 2, then we will return 1l, right? So we will either we will calculate the val, right? Either we will calculate this one, right? p n minus 1 f n minus 2 and the mod, the value we have, and finally we will put into our cache, and if that is the case, then we will return val. The main function is what? F of n, right? So f of n will check in the cache if that contains, then fine. For the base case, we will take n equal to what? 1, then we will return 1l. If n equal to 2, we will return 2l. If other case is there, we will calculate f of n minus 1, n minus 2, and 2 into the p n minus 1, right? p n minus 1, and the p n minus 1 is already, we have the function, right? We have calculated here, right? So this is the function we have got for uh, p of n, right? So p of n we have taken what? P of n minus 1 plus p of n minus 2, right? We have taken, and the mod function, right? That we have taken here. You can see this one. So pn, and this we have taken for f of n, right? So same function we will do here. We are calculating here f of k, right? We are calculating f of k. F of k is nothing but what? F of k minus 1 plus f of k minus 2 plus 2 into p of k minus 1, and this function is nothing but here, right? Then we will check into the cache and then we will return the val, and finally this is the function that we are calling. So we will take f of n and we will return, will convert into the integer, right? So we have not taken any extra spaces, but we are moving with the space that given we have n, the number of tiles we have given, that we will count. So all step we have to move from for the or n, right? So we'll take, we can say that the complexity of time will remain same for space and this, right? Because see, for the time complexity, if we'll say that this is 1, why? Because from top n to bottom 1, right? It will start from top 1 and we are going to down, right? 1 means there will be n non-memorized recursive calls to f and to p, you can say. So therefore, or you can say where each non-memorized calls requires constant time, right? And for that you can see, for we are calculating for f and p, right? And that is what, nothing but 2 into what? 2 into n times we are going. So we cannot say the 2 into n times, right? So we can say that this is nothing but of n, right? Of, if you will deep drive this one, so you can say that there will be 2 into n memorized calls for f of n and n memorized calls for p, right? We are calling, we are calculating and we are storing here, right? So there can be multiple calls for the memorization calls, right? And thus we can say that this is what? 3 into n, right? For the memorization we also call calling, right? This is required for the memorization call. But actually if we will add this one, right? 2 into n plus 3 of n, right? Like this. O of n, right? Then it is nothing but what? If we will sum it, this is nothing but O of n. And similarly, we are doing each recursive calls stack, and which contains at most n layers, right? Because we have hash map here, so these hash map will use O of n space together to store the result, right? And that's why their space complexity will also O of n. So guys, I think you have understood. If you have any doubt here, please ping me in the comment box and help me in growing by subscribing and sharing the expert funda. Thank you so much to watch this video, and please let me know if you want to go with other approaches also, right? Thank you so much.